Welcome back to our series on least squares linear regression. In the past video, we saw how to fit a simple model to some given data. We're going to continue this right now, and we're going to make the model slightly more complicated. So like we saw last time, we're going to have the same setup. Let's imagine that we're given some data, and this data is going to come in the form of a vector or a set of numbers that are known. This is f of k from k equals 1 through n. Right? So let's imagine we have k measurements, and they are shown here. Here's measurement number 1, here's measurement number 2, number 3, number 4, and so on. And we're given 10 of these measurements, so for x equal from 1 through 2 all the way to 10. And note the slight modification that we made with respect to the past setup. In the past setup, we call these coordinates x1, x2, and so on, so that we can be more flexible. But in order to simplify our lives a little bit, to write a fewer letters and make things a little bit faster, we're going to just imagine that x1 is 1, x2 is 2, and so on. We can easily rewrite these things in terms of x1 and x2. I just thought it would be simpler. So once again, in the past example, we worked with this model, where we were simply seeking a line of slope 0 that passed closest to all the points. In this example, we're going to modify a model, so now the model is slightly more complicated. It doesn't only have the intercept, but it also has a slope, so we can have different values of the slope give us different lines. In this case, we're going to have, for example, here's one slope, one line, here's another one, and we're going to ask ourselves which of these slopes or which of these lines passes closest to all the points. Of course, we're going to define what we mean by closest, but we can see visually here that the green line passes closer to the points than does the orange line. So let's exploit this concept a little bit. So again, here's the model that we're going to look at today, and we're going to fit to the given data f of k from k equals 1 through n. Like we did in the past video, we're going to use this q function, and this q will be a function that you input parameters a and parameter b, and you input into this function, and this function tells you how good a fit the line resulting from that particular a and that particular b, how good that line passes through the data. If this line will be exactly equal to the data, you can see that the error will be 0 all the time, and the sum of zeros will be 0, and the final error will be 0 for the fit. So this is a perfect fit. Of course, for real data, this almost never happens. So we must be content with finding the values of a and b that minimize this q function. And here, let's go ahead and do the same exact thing as before. We're going to measure the error as the subtraction between the model at that particular k and the data at that particular k. And like we did before, we're going to subtract this and square this so that we measure the total distance. We don't necessarily care whether the point is below the line or above the line. They're both the same error. So let's do this, and let's plug in what we know for the value for the model into the setup here. And if you take this model and plug it into here in this error equation, you end up with this definition here. So we simply went from here to here by plugging in the model that we know for the place of the model in the error function. And like we did before, right, one of the reasons we started by looking at the simple model is now in that example, our error function was only a one-dimensional function. It took only one independent variable in, and we could find the minimum of that problem. First, we noticed that it is simplified to a quadratic function, and we know from calculus, we know how to define the minimum of a quadratic function as simply the value of the function where the function's derivative is 0. Now we have a slightly more complicated situation, and the complication is the fact that we have now two variables here which pertains to the parameters of our model, in this case the slope and the intercept. So we have to find the values of a and b simultaneously that minimize this error function q. How do we do this? We follow the same exact strategy that we did in one dimension, and this also you learned from multivariate calculus, where now we can take the partial derivatives of q with respect to a and partial derivative of q with respect to b and set them to 0. And because this is a linear model in a sense that we'll discuss in a later video, when we plug in, when we compute the derivatives, partial derivatives, and set them to 0, we'll end up with a linear systems of equations, which we can use one of the methods that we discussed, like Gaussian elimination, to actually solve numerically. So let's go ahead and let's compute the partial derivative of q with respect to a. And so what we have to do here is apply the chain rule, right? We have a complicated function here that involves the sum and the square. Well, the sum is easy to take care of because the derivative of a sum is the sum of the derivatives, right? It's a linear operation, so you can swap the orders. But here we have to just take care of this nested function, right? The whole thing is squared, so we have to first differentiate with respect to the outside and multiply times the derivative of the inside. So if we differentiate with respect to the outside, right, this 2 comes out. And so here we go, we have the 2 out in front. And we have the inside part of the function. And we still have to differentiate the inside of the function with respect to parameter a. So the derivative of this inside part of the function only has a in this first term, so the derivative of the first term with respect to a is k, so we multiply by k. So from here to here, all I did is I regrouped these terms, right? So I have to first multiply this through for each element, and then I can separate each term of the sum to look at it separately. So first we multiply k to times k squared, and we take a out, so this is the first term. The second term we multiply k to b, but then we take b out, and that's the second term. The third term we multiply k to f, and of course take the negative out, so this is the third term. Likewise, we can take the derivative of q with respect to b now, and by the way, and then we set it to 0, right? And we seek for the values of a and b that satisfy this equation. But if we don't only do with respect to a, we only have one equation and 2 unknowns. So we must do with respect to b, and then we'll end up with 2 equations and 2 unknowns. Going through the same exercise, we first differentiate with respect to the outside of the function, right? So that 2 comes out front, like it did before. So here's our 2 out front. And then we differentiate the inside part now with respect to b. But b was by itself here, so the derivative of b, which is the inside with respect to b, is simply 1. It seems a little bit silly to write 1 here, but hang with me because later on we'll make a substitution where this will be more clear. So we'll just keep times 1 here, right? And like before, I'm going to go ahead and multiply this 1 through each of these terms, right? So first I multiply here, and then I bring the a out. So this is what happened here. This is our result. Once again, multiply 1 times b, so this is what happens. I'm summing over 1 here again. Summing 1 k times is simple. Summing 1 n times, right? So this k is really from 1 through n, and I stopped writing from 1 to n just because it's kind of cumbersome to write it every time. It's understood that each sum here should be from 1 to n. So so here's the second term, and if you do this through the third term as well, you have 1 times f, and we take the negative out, so this is 1 times f, and again we set everything to 0. So let's do one more thing and take these terms here, which are not functions of our unknown parameters, the parameters that we're seeking. So we're just going to move those terms to the other side and rewrite this equation. So let's do that real quick. So this 2 set of equations will be, and by the way, what I'm also going to do right away is we have this 2 over n multiplying all these terms, right? But it's equal to 0 on this other side. So I'm going to multiply both sides by n over 2 and essentially get rid of these terms, right? That they don't play a role in the solution. So we're going to end up with a times, I'll put this in parentheses here, sum over k, k squared, plus b, and I'll put in a parenthesis sum over k of k. This is going to be equal to sum over k fk times k. And let's do the second equation now. We're going to once again do a times sum over k plus b sum over k over 1, and this is going to be equal, and we'll put the other side stuff to the other side, it will be sum over k fk times 1. So here we have a system of equations. It's linear equations of two equations and two unknowns. And we already learned how to solve this, right? One thing we can do before we conclude this video is to separate this or rewrite this whole thing as a matrix vector multiplication, right? So let's do this. We're going to end up with a matrix which has these terms in parentheses here. So I'll just write the matrix itself, k squared, that's the first term of the matrix. This is sum over k, and this is sum over k, and this is the sum over k of 1. So this is our matrix A. My vector of unknowns here is AB, and this is going to be equal to the vector on the right hand side, which will be sum over k fk times k, and sum over k fk times 1. So here we can see that, and I can give these matrices some names, and the name here will be A, and let's call this X equals, let's say, vector B, right? So this is a vector X, and this is our vector B, not to be confused with the parameter B for the line, just to use the same nomenclature we had before. Right? So we can see how so the summary of what is discussed so far, we used a slightly more complicated model, and we did the same thing as before, where we defined an error function, plugged in the definition of the model in the error function, and then we differentiated with respect to the two unknown values that we had for our model. We differentiated the error function, and we did a little bit of manipulation, not too much actually, and we figured out that you end up with a linear system of equations where the matrix A is given here, and note that this matrix is symmetric, right? This value here and this value is the same, so if you take A and you transpose, that's the same as A. And the vector of unknowns is the vector of A and B. And on the right hand side we have all these values, which again, F is our given data, and K, of course, we know, we're summing over n terms K here. So the matrix we know we can compute. The right hand side of this equation, the vector B, we also know we can compute. What we don't know is this coefficients A and B, and this is the vector of unknowns. But once again, once we arrived at this statement, at this realization, we are essentially done. We can use one of the MATLAB codes, for example, to solve for this linear system and give us the parameters A and B that optimally match the data. By optimally means if I take the vector parameters A and B that I found to this procedure and plug it in here and compute this error will be the least value possible. So the error will be minimized and will give us essentially what's being plotted here in this green line as opposed to this orange line.